Okay, so welcome back to another video. In today's video, we have a second order nonlinear ODEs, ordinary differential equations, in full. So we have that pi to the power y prime of x squared is equal to e to the power y double prime of x times y prime of x. And of course, the way to solve, and we want to find a general solution y that satisfies this following ODE over here. Since this is a second order, basically we're going to convert this so that we can actually solve it as a first order ODE, and then perform some. We're gonna convert this so that we can actually perform like a separable equation, and then solve from there with the basic techniques on how you generally solve separable equations. So with that, let's start off by rewriting the following ODE as in Leibniz's notation of a dy over dx form. So then we start off by just rewriting. So this is pi then dy over dx square, and so this is just equal to e to the power, so this is d squared y divided by d squared x, and then multiply with dy dx. Right? Now I can actually just take the natural log of both sides, so then this means this our exponent will move to the front. So then here I'll write this out in full first. And then of course, as mentioned, the exponents go out to the front, so we have dy dx square, then this is multiplied by ln of pi, and this is just equal to, so at the ln of e is just 1, so we have the second derivative, so this is square, then multiply with dy dx. Okay, now let's actually, now what I can do is actually divide dy dx to both sides, so then I would just be left with the second derivative in respect to x, and then this is just equal to ln of pi multiplied with dy dx. Okay, so now the next step, what I'll do is I'll actually perform a substitution. So what I'll do is I'll actually call p, and then I'll let that define as dy dx. Okay, so now next what I'll do is I'll actually differentiate both sides in respect to x. So then I'll have dp dx, and then this is the second derivative, so this will be d squared y, and then divided by dx squared. Now let's just focus on the left-hand side for a sec. We can actually rewrite dp dx by using the chain rule, but really, when really I can actually differentiate the first part with respect to y. So then we have that this is dp differentiate in respect to y, and multiply this with dy differentiate that in respect to x. Okay, and now we set that p is equal to dy dx, so what I can do is I can actually just substitute this, and we have that this is just p multiplied with dp dy. Okay, so that'll just replace the left-hand side, so this is set to equal to the second derivative in respect to x, d squared y, and then dx squared. So I can just replace this with p, then dy over dx, and then that's just equal to ln of pi, and then we set that p is equal to dy dx, so it's just multiplied by p. And now next, you can just divide p to both sides, so now we have dy dx is just equal to ln of pi. So now things are simple here, so what we can do from here is, so I can replace the d squared y dx squared with p times dp dy. So let's see, then dp dy, and so that's set to equal to ln of pi, and we set that dy dx, we set that equal to p, so I'll just replace that with p, and then we can divide p to both sides, so we have dp divided by dy, and then it's just equal to ln of pi. So now things are simple from here because we have a separable equation. So now from here I can actually just separate our variables in respect to p and then y, and then set them equal to each other. So really I can just multiply, ln of pi is just a constant, so we're not really working much with here. But really I can just multiply the dy to both sides, and then we have the integrating in respect to p, so we have dp, and then equal to the integral from ln of pi dy. Okay, but then that's easy to see that this is just p on its own. But then we have y times ln of pi, y times ln of pi, and then plus some constant. I'll just enumerate this and call this k sub 1. Next thing is that p is dy dx. So now we can actually perform another separable equation a second time. So we'll just replace this, y ln of pi plus k1. And then I could just divide all this to both sides, so we could just be left with the variables of y and then x on its own. So then this is dy and then divided by y times ln of pi plus k sub 1, and then that's just equal to the integral of dx. And then we can see that you could do a u substitution over here, and you'll get that this is, we get u equals y times ln of pi plus k sub 1, differentiate that, it's just ln of pi dy, then just substitute the terms together, and then you'll get that this is, so factor out the 1 divided by ln of pi, and then differentiate the 1 over u, and just put the u back, so we'll actually get just 1 over ln of pi, and then multiply with, and I'll denote the natural log with positive values, so it's an absolute value. So this is y ln of pi plus k sub 1, and then that's just equal to x, and then with our constant, we'll denote this as k sub 2. Next is, now I can just multiply the ln of pi to both sides, so we're left with just ln of course, y ln of pi plus k sub 1, and it's just equal to x times ln of pi. You multiply ln of pi to k sub 2, but you know, that's still a constant, an arbitrary constant. So next thing, I can actually just rewrite this as a new constant. I'll denote this as k sub 3. And then next, I'll actually take the e base to both sides. So the e ln cancels, and we're just left with positive. So this is y ln of pi plus k sub 1. And then it's just equal to, so if you use your rules of exponents with the e to the base, so you're taking e and then that's the whole thing is the exponent. Using your rules for exponents, it's an addition, so you can separate the bases out. So it's e to the power x times ln of pi times e to the power k. E to the power k sub 3 is still a constant, and I'll just rewrite this as a new constant denoted as k sub 4, and then we have that this is just e to the power x and then ln of pi. And now next thing is that of course e to the ln just cancels, so we're just left with pi to the power x. So let's continue further. So ln of pi plus k sub 1, and then it's just equal to k sub 4 and then pi to the power x. And then I subtract a k sub 1, so then we have y ln of pi equals k sub 4 to the times pi to the power x. Subtract that with k sub 1, and now the last thing to do is just divide ln of pi to both sides. Now the next thing is just divide ln of pi to both sides, so we get that this is just y, and ln of pi is a constant, so we have a k sub 4 divided by another constant, so that's arbitrary, so I'll denote this as k sub 5, and then times pi to the power x, and then minus k sub 1 divided by ln of pi, so again that's another constant, but you know, we don't really need to put the negative, it's an arbitrary constant, so I'll just keep that as a positive, and I'll denote this as k sub 6. And there we have it. That's our general solution for this second order ODE, like so. All right, yeah, so that's pretty cool if you ask me.